So, let's talk about calibrations of alpha and gamma spectrometers. So, I firstly talk about alpha and then gamma ray spectrometry. So, the main point is that if you want to obtain quantitative results, then you need to do good calibrations. Of course, good calibrations are not necessary if you report only some qualitative things. So, main calibrations, they are energy, resolution, and especially efficiency calibration. Energy calibration means that you are able to identify the radionuclide, which peak belongs to which nuclide. Very simple. Resolution means that you are able to calculate peak area correctly. And this refers also to efficiency calibration. So, as I showed before, this is the equation for calculating the activity. If I remember the paper that you gave yesterday in page 6, there is a, please look at the page 6 equation. Bottom part of the page 6, there's an equation how efficiency is calculated and so if you solve efficiency from this equation, it gives you efficiency is N over T I, which is the gamma or alpha yield, and A activity. So, if you look at the equation, this N here in page 6, it refers to this, the count rate. This is count, and here it's a number of counts. Here is the time. And if they are divided, it's count rate. So the equation is basically the same. All right. So this N here refers to mainly resolution calibration. So you have to determine the area correctly. This energy calibration refers to this and this. I mean, you have to identify the nuclide I in question, and you have to find out data from the nuclide library. And of course, this refers to efficiency calibration. So, as I think Karunakara already said, that energy and resolution calibration can usually be done only once, because they are more or less stable. However, the efficiency calibration is a little bit difficult because it depends on the source properties. So it has to be not necessarily calculated in each case, but it has to be taken into account correctly. I mean, you should have a correct reference material with same geometry. Okay, let's look at the energy calibration. So, it enables to identify radionuclide and in question. And I said to you, you can find the correct data from the nuclide library. In often cases, linear calibration is okay. Sometimes you have to use, for example, second order polynomial. But it depends on your detector and amplifier or electronic characteristics. Okay, there are of course some other functions that can be used, but linear is okay. But the resolution. So it's important for n. So peak width here is a peak. Width is usually characterized by using full width at half maximum. So this is the maximum of the peak. This is so-called baseline, and this is in the middle of the peak. So, and this is full width at 10th maximum here. This is not very often used. This is often used, this WHM. But there is strong energy dependency, especially in case of scintillation detectors. At higher energies, the resolution is much wider than at lower energies. The effect is more or less same in high resolution gamma spectrometry, but not so stressed effect. So peak shape, it is usually Gaussian. However, shape of X-ray peaks is Lorentzian. However, we do not consider these Lorentzian things because it's only for X-rays, and photon energies are quite low. In those cases, we are in this course analyzing or using only gammas. In alpha spectrometry, the shape is in fact same, the main shape. However, there is notable tailing. In this case, there are 3 tails. This one here, it's a tail number 1, goes rapidly down to the 0. T2 goes slower, and this tail, if it will be taken into account, it goes very slowly to 0. So there are, in fact, many different ways how to determine peak efficiency calibration. So one way is shown in this paper that Karunakara gave us, Karunakara and his team, but there are several others. Efficiencies can be calculated by Monte Carlo simulation. There are software for that, but in those cases you have to know detector characteristics very well. You have to know detector dimensions, detector to source distances, thickness of the dead layers, etc., etc. Especially dead layer thickness, it's quite difficult to get. But it has a very big effect in gamma spectrometry. You can use also numerical approaches using standard radionuclide sources like Karunakara's teams use, and it's possible to combine all of these. I do not mention here our way. We do it by using efficiency transfer software. So our basic calibration for one geometry is done by using this way, basically in the same way as you do. But for each sample to be measured, we are using this efficiency transfer method. So every time we calculate new energy calibration, if we want to analyze the spectrum of each sample, every time. Okay, let's look at the efficiency calibration in alpha spectrometry. There are also several ways to do that. One way is to use tracer material. The tracer used in the present measurement, was it polonium-209? Yes. So if you know the tracer material activity, then you can calculate very easily polonium-210. Okay. So the efficiency is entirely determined by the solid angle subtended by the source detector system. So this is the solid angle here. And our software, ASI software, that you will get it from Stuk. This software can calculate it very, very easy. I will show it later. So the assumption is that there is no big energy loss in the dead layer or in the source. So I mean that alphas are not stopped in the source field, for example. So in case of this calculation, you have to know only detector and source diameters, and of course source to detector distance, and that's it. It's easy to calculate, basically. Well, in mathematically it's not necessarily very easy, but by using our computer software, it's really easy. So you will get this material, of course, and you can download it from this link. Or use Google, and using words Stuk and ASI, you can find it very easily. And this ASI software can determine the geometric detection efficiency. Perhaps I will check, is it, I will close this now. Let's check that, is it still open? No. Oh, I will show how it goes. Like it's this screen here. So what's the typical source to detector distance in your measurement? Is it
1 centimeter.
1 centimeter? Let's put it here. 10. All right. So what's the diameter of the detector or area?
450 mm and
Is it more or less same?
Yes, 450 mm.
Yeah. All right. What's the typical source diameter you have?
Diameter is 1 centimeter.
1 centimeter. Okay. Very easy. Okay. This offset means that it may be off the symmetry axis. Okay. Let's run the. So this is the efficiency. I think that you should test this software in your cases.
We have done the experiment and got the same value.
Yeah.
17%.
Yeah. All right.
Okay, this efficiency, it is simulating for, for an ideal case.
Yes, ideal
If
case.
your sample, for example, plating is not clean, there is some deposition of, for example,
Yeah,
iron,
yeah,
and there will be self-attenuation.
yeah.
How does this, how the software will account for that?
It assumes that there is no, how to say it in a very good way. It means that it assumes only that all alphas emitted from the source goes to the detector.
Okay. So it doesn't account for the imperfections in the source preparation.
Yeah, but the peak shape could be very wide also in those cases.
Yeah,
You
yeah.
just have to calculate all the counts.
Okay.
So this is only geometrical detection
Okay.
efficiency.
Okay.
I think that in your paper you call this as you call this as it was somewhere here mentioned intrinsic something. No, I don't find it.
That efficient equation they are not given.
Yeah. All right. But this is very simple. Let's close this one. So where are we now? We are here. So please note that there are several analytical ways how to calculate this geometric efficiency, but I can guarantee that this is the most easiest way to do the calculation, definitely. And this is correct, this number that you get out. We have shown it in our scientific publications. All right. What's this slide? Sorry, I don't remember why I put this slide here. So one thing which is very important is that you have to, if there are quite short-lived nuclides, then you have to take into account the decay, so you have to determine correct reference time for the calculation. But this is the same equation as this one in principle. So I looked through one of the papers shown here. Letters are very small, but some scientists studied the effect of if we are using different vacuum chambers. There are small effects. Okay, in this case, uranium-233, the effect is, well, not very big. The numbers here are so small that I can't see very well, but this is the source to detector distance, this one.
Is he getting 60% efficiency? CPS per alpha percent, this graph on the y-axis?
It seems to be CPS per alphas per second. Yeah, I guess so.
That's quite much. 60% efficiency is quite large.
You can check these numbers by using this ASI software. And please read the paper also. Let's go to gamma ray spectrometry. So, same methods as mentioned in the previous slides can be used in this case. In the next slides, I will show you how we do the efficiency calibration. But basically, it's very simple. So you calculate the efficiency like this. You have to know the number of emitted gammas per unit time, which is reported in the source certificate. And number of detected gammas per unit time is obtained by the measurements. Of course, you have to apply appropriate corrections, for example, reference time correction, etc. But very simple, basically. But in fact, it's quite tedious work if you want to do comprehensive uncertainty calculation. Then it's a very big job. So, as an example, in our lab we have 18 detectors. And characteristics of the detectors are a little bit different. Most of them are broad energy germanium detectors. Some of them are coaxial. Some of them are appropriate for Marinelli beakers. There are also some special detectors, one well type, one Compton suppression device, one alpha beta gamma coincidence system, one cosmic veto system also. We are measuring really several types of samples, any kind of samples, including individual particles. So how to do efficiency calibration in those cases, efficiency determination in those cases. So are you able in this laboratory measure samples with a low amount of material? What about point sources?
Point sources will have high activity, but we are able to even detect samples as low as 5 grams. This,
Is this 5 grams minimum amount of material?
not really. If I can put it in even a smaller beaker,
Yeah.
and the activity is quite high, I think I should be able to detect. But so far I have started from 5 gram. 5 gram of fun.
Yeah. All right. So, and my organization is responsible to do rapid measurements during an emergency. And this means that we have to do measurements quickly and do the analysis also very quickly. If the sources are high active sources, then we have to use larger distances. And we have very many different measurement geometries, or could have. These are the basic geometries we are using, so-called T beaker or Williams beaker. These are the volumes we can put into these beakers. So problem is that every case, in every type of sample, every amount of the sample, we have to determine new efficiency calibration. So it's in our case, it's just a mathematical way, so-called FTran software we are using. It's an efficiency transfer software. I will show its operation also later. I don't know, is it tomorrow or Friday or later, but let's see. So in our case, I have to think very carefully how to do with the efficiency calibration. Because we have so many detectors and so many geometries, and I think that we cannot operate like you are operating here. So, what's the starting point of the efficiency calibration? You must have certified sources. We have liquid sources produced by National Physical Laboratory from Great Britain. Your sources are, I guess, from IAEA. Yeah. These are the certificates. This NPL is a primary laboratory, so these sources are very well characterized. Typical uncertainties in each nuclide is of the order of 2-3%, something like that. So, by using these certified sources, our chemistry team made several calibration samples of different geometry, which gives us full traceability to the certified sources. So, as I explained to you, this is our basic calibration, so-called T20. This T20, this T means this T beaker, and 20 means 20 millimeter of liquid in this beaker. And if we are using this geometry, this V beaker, double V beaker, then we use efficiency transfer method. So only one calibration per detector. However, in case of Marinelli beakers, so the detector must fit here in this hole. We have two calibrations. but for the rest of the detectors, only one calibration. So, if you're doing measurements from each calibration sample, basically you should do very many measurements and use different sources which are made in the same way as the first one. This is to check that the liquid that we made or put into this beaker, they are always the same. But we have 18 detectors, so it's not possible to measure, for example, 5 calibration samples per detector. So that's why we very carefully measured only once, so that we get very big peaks, lower limit 10,000 counts per peak. So statistical uncertainty is less than 1%. I mean square root of this number. In terms of percentages, of course. So, efficiency was determined for each detector with full and traceable uncertainty analysis. I will show it later. So, we also have a lot of different reference sources from which we know the activities very well. For example, filters, sources with different thicknesses or diameters, and we know the activities very well. Because we are using this FTRAN software, we have to do it this way just to verify that the basic calibration is okay, and also the efficiency transfer calculation is okay. And once we have shown that it is okay for the certified reference samples, then in normal samples we can rely on the calibration. Okay. This is an example of one calibration spectrum. So it starts with lead 210 in the very beginning of here and ends at yttrium 88 here. So the peaks are well distinguished. However, there are some minor problems, but they are quite small. So you have to remind that we also take these X-rays, which are located here. Energies are close to 10 kilo-electron-volt. We can take these into account in some of our detectors, not all. So, how it is done in practice? We have a Excel spreadsheet form which was made for each detector. One Excel for each detector. So, in our gamma team we have around 10 persons. And my policy is so that I said to them, I made, can I show it here? I made this Excel sheet so that those other persons, they should fill only things that are marked as red here. I will explain soon. All other numbers are made by me. The point is that every at least high-level analyst should understand what does calibration mean. So it's not very evident always. All right, so it's like a training purpose. So the form includes full uncertainty estimation of the efficiencies. I will show this you, I guess, in Friday or Saturday. So the detectors are grouped according to their characteristics. This is because if we don't do this, the uncertainty calculation would be too tedious because of the large number of the detectors. So the measured raw activities that we get from the measurement, it's basically this one. It is fitted by using a log polynomial function, and lower energy is less than 120 kilo electron volts separately from higher ones. So this part is fitted separately from this part. Okay, and we validate calibrations by using different certified sources. Okay, let's look at the spreadsheet, but not very detailed way, because there are too many numbers here. So we used two sources, one with mixed nuclide source and one with only lead 210. This is for the mixed nuclide source, this part of the spreadsheet, and this part is for only lead 210. You cannot see the numbers here. You should check the PDF file, but these are nuclide names and their activities here. So what does the analyzer do? It just put peak areas and its uncertainties, and then this spreadsheet calculates the peak efficiency, which is located here in this part, and also this part for low energy gammas or X-rays. And you can see the uncertainties. In some cases, they are a little bit bigger, but in most of the cases, the measured uncertainties are quite small. So this is, so I call it raw efficiency, this curve here, because of this. So this part of the spreadsheet, the numbers are exactly the same as here, but I did fitting so that I can got a smooth curve. And then this part here is the uncertainty of the fit.
What kind of sample is this?
Sorry, what?
It's material. Is it water, solid?
It's almost water. Little bit acid there.
Oh.
So how the fitting is done? It's in fact quite complex process. I will show it here. Sorry for you. I will. Okay. I will write down. So these are the measured points. Uncertainties are, in most cases, they are more or less the same in each case. Thanks. So how I did the fitting. So first I did the fitting using log polynomial function by using these reference values. So the curve is like that. Then I added these uncertainties to the measured points and made fitting using these values here, or these values down. Like this. Because sometimes fitting process is quite mathematically difficult to do. So final efficiencies are here as a function of energy. In this case, starting from the energy of 6 keV and ending up to 3 MeV. Let's look at the data. This is the mixed source. So in the top part of each Excel, we have how to say it? We put there all basic information of each measurement. Who is doing the analysis, what's the dead time, how long does the measurement take, etc., etc. This is relevant basic data that must be taken into account. Then, according to the nuclide-specific data and the reference material, this is the information from the certificate. It's this part for each nuclide. This part is number of counts of each peak and its area uncertainty. These are reported by the analysis program. We are not using Jenny in gamma ray spectrometry. We have program of our own, so-called Unisampo Shaman. It's well, quite good program. Then there is a part of coincidence correction. It's a quite difficult area. I will neglect it here, but we took into account coincidence correction too for each nuclide. In some nuclides there is no coincidence correction. For example, in case of cesium-137, there are no corrections for that. And this part is quite interesting because one of my students, in fact, made this part in his Master of Science thesis. This is the uncertainties on the basis of measurement geometry and beaker. For example, beaker bottom thickness might vary. It is possible. Beaker diameter may vary, not much, but a little. All these things are taken into account in this area. And then we get the final raw efficiency as a function of energy or different nuclides. Then I explained how I made uncertainty fitting this way here. This is the upper limit information, lower limit information, and final efficiency. So you do not need to look through all these numbers. I just want to give you an idea how we did it. There are different ways. But I think that this is quite, at least from our point of view, it's quite good way and quite reliable way, because now there is a full uncertainty estimation, which is reliable. I think so. Because all relevant uncertainties are taken into account. So, how to validate the original efficiency calibration? Okay, as I explained, we use different reference sources. In this case, we use detector known as G5. It is just a name. All right, so we know the nuclides present in the reference source. We know the activities of the reference source here. And then we make a measurement for that reference source, put the activities here and compare the results to the reference source. In this case, there are 3 different reference sources. So how we do, or how it looks like this efficiency calibration in our analysis program. So this is energy, I mean the horizontal axis, and this is efficiency here. So as you can see, we are not using smooth function. We are using interpolation between each determinate value. Are you using functions in your efficiency calibration? I mean that if some nuclide is in this area, around, let me say 40 kiloelectronvolts, are you using function or a linear interpolation?
We use linear.
Linear, yeah. All right.
But the software has the option for both.
Yeah. Yeah.
It has an option called by dual efficiency, dual energy.
Yeah.
For the higher energy one side and
Yeah. So do you have any questions on gamma ray point? You can later check all these slides, and please contact me later if you want to know something. But that's our way. There are several other ways to do things.
So, in one of the graphs, efficiency graphs, you showed the peak curve and then a total curve.
Yeah.
So what is a total curve?
Total count, that one, yeah. Total count, so-called total efficiency. It takes into account, so the spectrum, it takes each count into account of the whole spectrum, and it is used for coincidence correction calculation.
It means it takes account of even
It summarizes all the counts. So it's an integral. I don't explain it here because it's quite complicated issue with this coincidence correction. We have no time for for that. So, okay, but
I have a question.
yeah, of course, please.
You are using multiple sources, right?
Multiple,
Sources.
yeah,
But the half-lives are different, right? So
Yeah.
some will decay faster.
yes,
So you need to
That-
change the sources
yes,
regularly.
yes. In each case, we take reference time into account. So in each case, we calculate the activities to a certain reference time. It has to be done like that. How to explain? It is possible that some nuclides, short-lived nuclides, might die totally away from the sample. So then let's look at the example here. Is here any? Okay, for example, I think it's this sample here. I don't remember what is the sample for it, but for example, this cerium isotope tin, chrome, tin, strontium, they have decayed off. So we do not take it into account in this test case. It's not a problem in this case. Okay, they have died and we just neglect them. But remember that this is not a efficiency, our basic efficiency calibration. This is only for checking that our so-called T20 calibration is correct, because this is our starting point, this T20 calibration. Just to check.
So originally first time when you do, you use all the.
Sorry about the noise, yeah.
Originally when you do for the first time, so you use a high strength sources.
Did it got the point? Sorry.
So when you do it for the first time,
Yeah.
all these sources will be there in the sample.
In the first calibration sample, all the nuclides are there. However, these samples shown here, reference samples, they are perhaps, and they are indeed more old sample.
Okay.
They are just to check that the primary calibration is okay, and our efficiency transfer calculation is valid. Just checking. I hope that you understand the idea of this. It may sound quite a strange way to do things, but I can guarantee that in our case it's the best possible way to do the correct calibration, because of the great number of gamma ray spectrometers. All right, let's look at the role of low energy alphas or gammas. So, let's look at first alphas. This is lower energy part of a gamma spectrum, alpha spectrum here. So, this is for americium-241 and very thick sample, 0.1 millimeter thick. Okay, it's in terms of alpha spectrometry, it's thick, but of course it's very thin. So here are signals from electrons, betas, and electronic noise. How to calculate peak area in this case? Any idea? Well, this is not an easy issue. However, it can be taken into account in this by using this ASI software. But we do not, in fact, know basically how many counts are, in fact, here, which are below the energy of 0. I mean, which are totally absorbed, because the sample is so thick. So the answer is, I think that there is no easy answers. You just have to calculate how many alphas are totally absorbed. But this is an extreme case, this 100 micrometer thick source. In case of gamma spectrometry, this is okay. This is part of our calibration measurement. So we have nuclide, lead, americium, cadmium, and a lot of X-rays here. So basically, we cannot do the spectrum analysis here because this is too complex area, and this rest part of the spectrum, there is dozen of radionuclides. So you are starting your analysis up from 30 kiloelectron volts. Yeah. So if you have only 1 or 2 nuclides in your radionuclides in your sample, then you might use that part into account in the analysis. But normally there are many of them. And for example, in the case of electron capture decay, the X-rays may be in true coincidence with gammas, which might cause additional peaks in the right side of the gamma peaks. However, in the efficiency calibration, we used only lead 210 liquid in the basic efficiency calibration. So this is 46 kiloelectron volts, and these are the X-ray peaks. Now, in this case, when there is only 1 nuclide, we can take these peak areas into account in the efficiency calibration. Like this. I look at the data from nuclide library. I put some peaks together, like, for example, this peak number 1, located here. It consists or contains 2 X-rays. This peak number 2 contains 1, 2, 3, 4, 5, 6 or 7 sub-peaks, if you call it like that. And in this item 3, there are 4 peaks. I fitted the areas using our analysis software, and then I calculated the efficiencies here. So note here, 10 kiloelectron volt is the lowest energy in practice, but normally we do the analysis as same as you do above 30 kiloelectron volts. These are used only for the coincidence calculation. Okay, is it? No. Okay, this is it.